Okay, why don't we get the show on the road here? I am just delighted to have our next speaker. I'll let her introduce herself and give her a little bit of her background. This is a subject that is dear to my heart and was one of the primary topics that I wanted to cover for this particular event. The amount of innovation and the amount of money that's going into these edge device deep learning is very high at this time. There's a lot of interest. There's new companies coming out with new classes of hardware. There's new software algorithms to take deep learning, machine learning, and bringing it out to the edge for a number of different reasons. Some of them business reasons, some of them technical reasons, and a variety of things that many of you probably have read about. So with that, I would like to introduce our next speaker, Heather Ames, and go to it, Heather.
Good afternoon, and thanks for inviting me to this event. It's been really great. So Dan asked me to say just a little bit about myself before I get started. My name is Heather Ames. I am the co-founder and COO of Neurala. We're a startup here in Boston. We've got about 35 employees at this point in time. I have a PhD in cognitive and neural systems, which is basically computational neuroscience out of Boston University, which is where I got a lot of my training in this. And that was actually before deep learning was even a thing that we talked about. So a lot of my background is much more focused on biologically inspired algorithms, and that's kind of at the angle that we came at this when we started our company. So I'm going to start off my talk in sort of a trilogy that we sometimes like to talk about, particularly when we talk about deep learning and robotics. And basically, it's like a recipe. So what are the three key ingredients that we need to create intelligent robots? And by intelligent robots, I mean robots that are perceiving their world, making decisions in real time, and then acting upon those decisions. So we have an inexpensive body. You know, we've had a lot of discussions of that so far today. What kind of bodies can we have? Actuators, the physical body of the robot. Powerful brain, this comes in the components, the chipsets that are residing in the edge devices on these robots. And then the smart mind, which is where our company's expertise comes into play. So these are some old pictures, actually, but you know, we like to say there's the coming of the body. There's so many cool robots out there today, from toys to drones, self-driving cars, vacuum cleaners, you know, and on and on and on. Like this is a fun space, and it's an exciting space to be in. And we also have a lot of sensors, just a few listed here, but even this has been a hot topic at this meeting as well. So what kind of sensors do we have on these? What kind of information are they bringing in? What's the resolution? How quickly can we process it? All these interesting questions that are really coming into play. But where do we compute all that data that's collected from those sensors? So we have lots of these sensors working within a robot, but we really need to process that data on the edge. And by the edge, I mean in the device. And this is because if we don't process it on the edge, we're storing the data, we're transmitting data, processing it somewhere else, sending it back to the robot, and then doing something with it. That would be a horrible robot to have. It would not be productive at all. And so it would just, the communication bandwidth issue alone would be a problem. So we know that the edge is the only option that we have to create true intelligence within these robots. Luckily, compute power has been so much fun to work with. When we started our company in 2006, we started on big GPUs. So we took AMD processor at that time, and we were doing assembly language coding on it of neural networks, okay? We called up NVIDIA and we said, hey guys, we think we want to run our neural networks on your GPUs, and they hung up on us, all right? So this was before CUDA, okay? So we're really excited about where it's gone, because at this point in time, our CEO, Max, sat down with my other co-founder, Anatoly, at a coffee shop and said, look at my cell phone, which was like this clunky Windows thing with a stylus. There's going to be a GPU in this, and we're going to run our networks on this someday. And Anatoly like spit his coffee across the table. No way, not going to happen. But here we are, right? We have GPUs in our phones. We don't just have GPUs in our phones. We have the other chipsets, more exotic chipsets that are being developed all the time that offer big advantages to developing neural networks and deep learning. in mobile devices. So it's really a great time to be in this field. So we can say, hey, we've got a brain and a body. They're here, right? They're enabling technology. So where's the mind? I don't see any robots walking around here today. We do have a lot of work to do. But let's take a step back and let's look back into AI and the evolution of deep learning. Just a little history lesson. So what is AI? We took this off of Wikipedia some time ago. As machines become increasingly capable, mental facilities once thought to require intelligence are removed from the definition of AI. Therefore, AI could be considered anything we ourselves can do, but we cannot make our machines do for us yet. Think about that. It's kind of fun. So the bad news is AI is a measure of a lack of natural intelligence. The less we can make machines do, the bigger our field. The good news is that we're never going out of business because there's so much that we can do for machines to make them smarter. So back in 1943 was really the first instantiation of what we would call sort of a neural network architecture. And these networks were configured to perform arbitrary logical functions. They were initially designed for computing architectures, but lost to the von Neumann paradigm, and so kind of got pushed aside. The main points in these networks still hold true today, which is that an activation is computed as a convolution or a dot product of an input vector and a weight vector, and the output is computed using some nonlinear function of activation. So it's just the basic building blocks that we still carry through today. And this original version had no learning in it at all. It's a very simple network. We then evolved to create perceptrons, so very early stage backpropagation networks. These had fully connected layers. They had distributed representations. Each new input during training would lead to a change of all weights for all nodes. And this can lead to an issue, which we'll talk about a bit, called catastrophic forgetting. This means that each new input has a potential to erase the memory of all previous inputs as it's learned. So the main solutions to overcome this problem have been to retrain with new inputs interspersed with the old inputs, so essentially retraining the entire network, and also to completely change the distributed representation we find in them. And then the learning rule we used in these often was backpropagation, which leads to two other problems of getting stuck in a local minimum or overtraining based on certain inputs to the system. And just to dive in on catastrophic forgetting, this really is a problem with distributed representations where many neurons are involved in correct classification of every object, and many weights are also important for each classification. So every new object that is learned will perturb all the weights and hence cause forgetting across the system. So that's really the big issue there. And then we go deeper, right? So this continues to develop. We continue to add more layers to the system. That early perceptrons was just 3 layers, very small, easy to compute, although not at that time. And then initially, even with these deeper networks, we would train them layer by layer. It would take forever. But with GPU computing, we can now train the whole network using multi-layer backpropagation. Some of these layers are fully connected. Some are convolutional kernels. They all use some sorts of distributed representations, but still retain the catastrophic forgetting problems of their predecessors. And we can extend this further so that we have even extended multi-layer perceptrons with feature detection layers that have convolutional kernels and classification layers that are still fully connected. So now we have layers that have functional purpose. And then we have different tricks that we can add, shortcuts, multi-pass deconvolutions for different tasks. And when these systems are trained extensively on large data sets and with particular configurations, we can actually find that we can achieve superhuman performance, but on very specific tasks that they're trained on. So, with all that we have learned from these networks, deep learning is not enough yet for intelligence. Backpropagation, in its purest form, cannot learn incrementally, and it cannot learn on the fly. While DNNs outperform humans on individual tasks, they have a long way to catch up with us. So it's too early to demote our brains from being the most intelligent computers we are aware of. So rest assured, machines will not take over our jobs. All right, so let's take a step back and then look at the training paradigms that we see in these deep networks. There's two main components necessary for these deep networks right now. Very large data sets, tens of thousands, hundreds of thousands of images per object class. Lots of computing power, okay? Tons. Why? Because when we want to learn something new, we have to combine that new information with the old data set that was used to initially train the network and retrain the whole thing. And this is going to require powerful servers, lots of storage space, and it's going to take a lot of time. So let's take a look at a few of the specific examples of how these networks can be used, particularly those that are related to what my company does, which is in the field of visual processing. So the first is whole scene analysis or object recognition. So in this picture, you would look at this and you would say, there's a bottle, there's a cup, there's a cube, it's a desk. You have various ways that you could classify this image. So whole scene analysis, object recognition. On the right is the 2015 state of the art, where you can see that we have networks that supersede human performance here. All done on the server, though. And here's an example of ResNet. This picture here shows 50 layers, but this goes up to 1,200 layers. That's a lot of layers for computation. That takes a lot of power. So one of the innovations in this particular structure is shortcut layers, because the issue when you get deep, so one of the things that's been done in deep learning is you just keep adding more and more layers to improve your network. But because of the back propagation of the error on the second pass, that error propagating back through the network gets smaller and smaller and smaller, and it creates problems because by the time it gets to the bottom layer, it doesn't really have any information. So there's different architectures that have been designed to overcome that issue, and this is one of them. So today's AI or deep learning training regimen is train once, and that's it. You're done. No additional learning or refinement of knowledge. So you use a large server, massive data set, millions of iterations. So we set these things up. They're training for days. You come back and check to see if it's complete. And what you get at the end is a fixed brain. This would be like the following example in us. So what would be the human equivalent? Let's say you went to college, you studied robotics, showed up for work day one, you never learn again. All the knowledge you have through your entire career is what you learned in college. You can never add to that. Now, think about how great that worker is going to be at the end. So that's kind of what we have when we deal with fixed brains in a dynamic world. And this is just to illustrate the training of these conventional DNNs. Millions of training samples, takes a long time for the performance to converge and the training to be complete. So the three fundamental issues of DNN development, particularly for edge learning, is there are massive data sets needed to make generalizations about the world. So that means massive storage is needed. That would be pretty tough to carry around in a robot. Inability to update learning without completely retraining. So your robot encounters something new as it's moving around in the environment, and it can't update itself. What do you do? And finally, because of all this training is quite extensive and computationally expensive, the training must occur at a centralized computing server or cloud. Early in one of the earliest pitch decks of Neurala, we had this great video of a robot with this giant cord hanging out of it connected to a supercomputer. It's not that bad today, but it gets the point across. So that's not really going to work. So traditional DNNs have very severe limitations for robotics. But what if we could capture the human ability to learn day after day in a robot through software? And just to reiterate a little example on this fundamental issue on these traditional deep learning systems, imagine if you trained a network to recognize produce in a grocery store, and you put it on a robot whose job is to sort produce. But the guy who trained it, he hated apples, so he didn't train any apples. Well, then you put the robot in the store and all of a sudden you find all the apples are in the box of pears. And now you need to relearn that information. Instead of telling the robot, presenting him apples, this is an apple, put these in this box, like you would with a worker, you have to send it back to the factory and start over on the training. So this is really about how can we improve that efficiency and allow things to actually work in real world problems. So how can we add new data to existing DNN knowledge without forgetting the old data? How can we do this without powerful servers and cloud access and do this in real time on a robot? And we have other issues that we've encountered, and this is just a couple of examples that we think about when we work with our clients. So in the first column, clients don't want to share their data. Clients don't want us to keep their data when we're done training. They want to keep their data to themselves. But if we have to retrain an entire network using all the data that's already been trained on the network, how do we overcome these issues? Where do clients store that data? How do they do the retraining? These are big problems that people are asking. Also, if you think about in the toy space, if we were to develop a robotic toy and do training in the factory on other toys so it could recognize a ball, a jump rope, and whatever, that's easy, that's fine, we can do it. But a lot of these companies would like to have toys that recognize their owners or pets. Well, then there's a huge privacy issue because I don't think any of us want to have robotic toys in our kids' bedrooms that are connected to the cloud in order to add learning in that system. So we want it to be all done on the edge. This also ensures privacy, and that's a really important point for many clients. So what our company does is we develop something we call lifelong deep neural networks. And we put that into what we call the Neurala brain. So we want to learn like human brains do. Train once, deploy on the job, learning day after day, and the brain can get smarter at each step. So the learning evolves with the system and on the edge. Now, luckily for us, our paradigm also trains really quickly and uses less training samples. So we can have a brain, as we like to call it, ready to use within the matter of seconds rather than hours. So this is just a short video showing our system working. Here, Emily's learning a mug. She's just labeling it, and she just has a few seconds of the video frame to learn it. Then she recognizes a different mug, or she calls it cup. And then she can learn another object, car, learns it right here on the device. And now it recognizes the car. And then on the right, I have just a quick table of some testing that we've done internally, comparing a traditional DNN, just kind of off-the-shelf system with our LDNN technology. You can see the training time difference, 15 hours versus 24 seconds. Significant difference in the image presentation. You'll see in the precision, it drops slightly in LDNN. But this is the base deployment model, so we do take a few hits on percentage points for precision, which we can easily make up when we move to the learn on the fly mode. And you'll also see our memory footprint is pretty small as well. The other cool thing that we've realized is we get generalization much earlier in our system than some of the deep networks have gotten. And this basically shows here that when we did a study of objects with 36 images of those objects, after about 8 image presentations of each object, we sort of reached our peak performance. So it really wasn't necessary to train any further. So that's also really nice. Then we can take this a step further. So it's really great if a robot's traveling around a room and it can see various objects it wants to go after or knows what kind of environment it's in. But maybe you need to know where those things are at if you're doing, avoidance or any of those other activities. So this shows you, again, that picture. But now we're actually putting a nice box around the various objects in the scene. There's 2 traditional approaches that are used on this. One is called a region proposal approach, where you basically do 2 passes on the system and it finds regions of interest and then hones in on the classifications. There's also a single pass approach, which is much faster, but it's more complex and a bit less accurate. And so we've been working in this space as well. And here's a few videos. This is some drone stuff. So on the left is showing a system that we trained up in a virtual environment, and then it's showing you way back in the horizon other flying objects that you don't want to run into. So tracking and following. And then on the right is a sense and intercept. So this is from the ground, and it just shows learning that object and tracking it through the sky. We've also been looking a lot lately with drones. So drone-based inspections is a really interesting area for our customers. So this is from a trade show a while back. And here the drone is looking at an antenna tower, and then it can classify the various objects on the tower. And also it can identify damage. And so then we've done, some more work on this. We have a lot of customers that are interested in insulators, which this will show you out in the field. And they're also interested in finding damage on their assets and inventory within these different structures. And being able to identify those things and then go in closer to get a closer look at the inventory to see if it's damaged, what kind of damage, how severe is the damage, and so forth. So this is where we get a lot of interest as well. And here we really need this edge learning and processing in order for it to happen on the drone. We've also done this work with the Lindbergh Foundation to work on detecting poachers. So this was a system on a fixed wing drone to detect elephants and then poachers with IR video. And then of course, we can come back to the ground. And there's, many instances and networks like this that we've been working on, finding pedestrians, cars, trucks, cyclists, and other vehicles in the scene to either help with navigating, collision avoidance, or just identifying things. Here's a few examples. And then we'll take it one step further. So another area that we've been working a lot on is object segmentation. So not only where is the bottle, but what are the exact boundaries of the bottle in the scene, and the cube and the cup. We have a current system architecture that we've been working with. It has these 7 categories, so bodies of water, sky, plant, pets, people, flowers, and buildings. Here's some of the stats on it. Our accuracy is improving every day. But interesting to note is the model size, 3.8. That's great. This is definitely working on the edge. A lot of these segmentation systems that you'll find today are really hard to push down to the size to be able to run effectively on a mobile device. So we're really excited about this. Here's some examples of the segmentation so you can see what it looks like. There's masks over. So there's like a yellow mask over the cat here. The next one, the green outlines the building and the trees and the sky. A few of the people ones, it's a little hard to see. Over here, we have a city in the background on the hillside with like a dad and a daughter, segmented, as well as the vegetation. So this is kind of a lot of stuff that people are interested in the image processing world, particularly in consumer devices. There's a lot of interest in this in terms of enhanced photo editing. So this has less sort of, I'd say, application directly to sort of actuating robots, but more in the world of sort of photo and video enhancement. And then this video just shows some of the work that we've done in this space, in particular with mobile devices. So you can see the segmentation working on the live video. We are currently working to add our LDNN technology on top of this. So this is really for a photo editing case where not only is this running in real time, segmenting the image, but also you can then learn customized filters or other things based on user experience in real time on the edge. So you can make those modifications as a consumer. So I would argue that the mind is coming. We still have a long way to go to bring it to the place that we have, I guess I would say in the body and in the brain. But there's been a lot of amazing advancements that have really been pushed forward by those developments. And one other advancement that we've been working on, which is a lot of fun, is called brain melding. And so this is basically merging knowledge from multiple robots on the fly. So a lot of robots, we don't really want them to work on their own. We want them to work together. We want them to work with humans. And we want that information to be able to be transferred. So it would be nice if you were working collaboratively with a person that you could download what you've learned about the situation and just hand that download over to another person. But instead, we have to have conversation. So with robots, we could really just download that information or merge it. So that's what we've done. See if I can play this. Maybe. No, this video is broken. So essentially, oh, there we go. So in the first device is learning this banana. Very simple. So a few frames, just kind of jiggle it around. That's the learning process. Recognizes banana. We take this information, we send it to a centralized location, and we send that information back out to a third device. So that's the merge on device. And we take another device and we learn Emily. So that's the learning, just move it around a little. Recognize, so now we can see Emily. Send that information to a central server. Take out a third device. We're going to pull that information from the server. And now that third device can recognize the banana. And it can recognize Emily. That's the basic concept. Share that knowledge. All done on the edge. And we have one collaboration that specifically looks at this with Motorola Solutions. So Motorola is interested in the use case of finding a missing child in real time. So you may be in a situation where it's very crowded, urban area, and a mother may lose track of her child, such as this one right here. This is a very fluid and real-time situation where she may come up to a police officer with a photo of her child or a short description. He needs to learn that information on his police-worn body camera, send that to Central Command, and then push that information out to all the other first responders and devices in the field. So now you can imagine all those police-worn body cameras on all the first responders in the area are doing this processing. So they're looking at all the people in the scene, trying to determine if they can find the child of interest. And that can only be done with learning on the edge, because you have to make that learning with that single encounter between the police officer and the mother. So here is a picture of our current team. Like I said, we are about 35 people. There's 3 of us that founded the company. We were 3 Boston University AI professors. We've worked with NASA, DARPA, Air Force, and many other companies. We started in 2006, but we really launched ourselves as a commercially viable company in 2013 when we were part of the Techstars program. We are always actively hiring people in the space, particularly those specialized in deep learning and AI. And that's the team, and the little baby's mine. So she's not a robot. Okay, thank you. And now we have time for questions. Yeah.
How possible it would be to transfer this to recognizing materials? Like, you recognize the corrosion based on how it looks, but could you recognize a cut up apple based on smell or other material properties?
Yeah, so we've done a lot of work in the earlier days on multisensory integration. So combining information from different sensors to make these decisions, but we haven't done a lot of it as of recently, just based on purely the market push for staying in the visual space. So, yeah. Yep.
So, thank you very much for the presentation. This system on the device, what would be
So the LDNN? Yeah, so that's our proprietary technology. So I'll give you my business card. But in terms of the initial data set, so one of the things that we really push forward with the LDNN technology of the object recognition is very little data is needed. So that was kind of the purpose of the demonstration where Emily was just doing a few frames around an object. And when I showed that you can learn after only 8 instances. So it's really about how can we learn quickly and make generalizations about the world, and then we can incrementally add on top of that as we encounter things.
So when you're doing that merging, so basically you're merging the training data set and then building the model over again?
No, we're doing a consolidation, not in the training data set, so it's not using any of the data. It's using the actual learned knowledge in the system, and it consolidates it at that level.
Yeah, to follow up on that question. So you have the same architecture on all the devices, including the server, and all the different devices are running with the same configuration.
Just the edge devices are running with the same configuration. The server is really just the holding cell.
Doing some magic and then
It could just as easily be communication protocols in a different way. Just because that's in an early stage of development, that's the easiest thing for us was to throw it up on AWS to make that merge. You could easily imagine a situation where the merge occurs on another device, or through Bluetooth connectivity. But we just kind of shorten that circuit. Yep.
What happens if you put a specialized preprocessor on the system so that the data occurs not as in the like a cell phone, but you've already done image detection, you've fed in infrared, there are lots of other forms of information.
Yeah, so part of the foundation of the LDNN technology does reside in a lot of the feature extraction that benefits that you get from DNN technology. So if you were to feed something that was already pre-processed, it might not make much of a difference. We haven't tried it. I like to say that one of the advantages that deep learning has brought to the field is it completely destroyed my PhD dissertation, which I spent 90% of it on feature extraction, and then feeding that into networks. You no longer need to take that big step. That's what deep learning gives you in software. Yeah.
How would one work with you? You provide a DLL that we bring into our software and we make calls,
Sure.
our features.
So we have different levels of engagement right now, depending on use cases. We're actively working right now to make an online portal for you to do this sort of learning in real time, just online. We've engaged with a major cell phone manufacturer in which we just give them libraries with some very thin software layers around it. That's how they wanted to integrate it. We're working with a drone company. They have a copy of our SDK. We've worked with another company where we built them an application. So we're still very early stage and we're working on our business model. So there's many ways that we work to engage with people. Yep.
You mentioned that the network can actively update when deployed. Does that require active user feedback?
Yes, it does.
And is there a concern that there could be misinformation because of it?
Absolutely. Yeah. So particularly when you think about the brain melding case, and again, that's very early work for us, you would want to imagine a situation where you have an administrative portal, a workflow manager, because the information is going to be as good as the person who taught it that information. So you want to make sure you don't dilute the message. Sure.
Question about feature extraction. Let's assume I'm not interested in pictures, but I'm interested in patient records.
Uh-huh.
No two conditions will even describe the same genome coming from the same source.
Yeah.
So there's no picture, there's no consistent data set, but there is actually a consistent body of knowledge behind the conditions of recognizing. How do you deal with that?
Yeah, so that's in the text realm, which we haven't been working in. But that really starts with the labeling of the data. So if I think of the analogy in the image world, When I showed you the information on the segmenting of the image, in order to teach systems how to do that, you have to go in and manually hand label the entire training set and be very specific about what it is. And so when you feed these systems anything for the training, if there's 10 ways to describe an ingrown toenail, they're all going to have a tag of ingrown toenail. And then it's a matter of extracting the relevant features from the data to determine what contributes to understanding that it's a toenail, right?
Be extended beyond that.
Oh, go ahead.
Be extended beyond feature extraction. So, suppose you want to look at activity tracking.
Yeah. So, I mean, a lot of the work in deep learning is just emerging. I'd say the last 5 years, we're really starting to see what it can do for us. So it's just the beginning. Yeah, just the beginning. Yep.
So you accepted you're able to identify the boundaries of certain relationships?
We're not looking quite at the relationships yet. Yeah. We do have a project underway, though, that will be digging into sort of 3D reconstruction, configurations of different components in a 3D space. So then we would get the relationships out of that. Yep.
I'm sorry, something I wasn't certain about, going back to how this actually works. So is this a pre-trained model? Is that what happens? And so when then you take it to the edge and then you're looking at the car, I don't remember exactly the example, but it now then is going to be able to associate that and recognize that, oh, that's a car.
Yep. So it has already some learned information on the back end that's compressed so it can operate on the edge. We put it on the edge and now we can learn there.
And then the question before about the merging information. So then when you are then, I don't know if this is the word, retraining on the edge,
Mhm.
the information that you're gathering, the question before you said if somebody gives you bad information, now it messes with the model. Is that something that is a common issue that you would have to deal with?
Not right now. I think that gets like quite theoretical. Part of the reason is because people can call things differently, and yeah, I was just I heard a story on NPR talking about bias with this whole Starbucks thing, and the person on there was discussing about how when you have a group of people contributing to a conversation, then the group can remove bias. So it's kind of tough to tell sometimes when you label something. If that label, is right or wrong necessarily, or how you would exactly classify it. And there's good things that can come out of that and bad things. So we haven't played a super ton. Again, that's really early, but it's something that needs to be evaluated in terms of how do you pull in information, whether it is in the workflow, adding in like a supervisor, that's saying, this is one of my best workers that has trained this robot, this information is valid, or hey, this guy just started, he has no clue what he's doing, I don't want to screw it up, type of situation. So I think it's really a workflow management issue on how you want to deal with it. Yep.
How do you ensure the reliability and the credibility either just post-training or as it continues to evolve?
Yeah, so when you get it, right out of the box, the credibility is there. We've done extensive testing and we have the feature extraction that we wanted to have for the system. What happens after that is really in the hands of the users and the customer on how they want to use it and how they want to add that information. And so that really becomes a workflow issue rather than a technology issue. So how people want to use it and how they want to validate that information. I don't know what that one, the segmentation one is done on, let's see. This one here, so this model size processing time was done on an NPU processor, a mobile NPU processor. We do benchmarking in just a laptop environment, TX1, TX2, Snapdragon, and a couple of NPU style things.
And you do some training, like when you have multiple contributors?
Not yet. We're going to work on that. Yep. For this one, we were at 352 by 352. Yep. Yeah, it just, obviously it changes those numbers, but again, this is like a very small mobile phone processor we're talking about with an MPU hybrid solution. So we could change out that, increase the resolution, go to like a TX1, TX2 environment and still get the same processing speed, and it's still at the edge. Well, I'm sorry? Yeah. Yes. Yes. We get a lot of high-res images. Yeah. This particular use case is just optimized for the mobile phone case. Yep. We did a little work with acoustic data, not a ton. Yeah, I don't have any great conclusions from it. Yep.
Same question.
I'm sorry? We're currently working on a project right now. Mm-hmm. Yep.
Who else is working in this space and what are you guys
Lots of people are working here. So the big thing that we're doing is edge processing, learning at the edge. Most people are really struggling with getting networks small enough to process at the edge in a speed that does anything reliably, and then being able to learn at the edge as well. So other people, I mean, you have obviously like TensorFlow is out there. You have a lot of open source frameworks that are out there. There's a variety of startup companies popping up every day working on it. All the big companies are working on it. Everybody has an internal team working on it. It's fun. Yeah?
You mentioned TensorFlow.
Yeah.
TensorFlow, you can kind of create your own architecture and
Yep.
create your own network. Do you have some flexibility? Or you
With
have a hard code?
within the SDK framework, we do have flexibility that we can offer people. We also support TensorFlow models, so if there's things that you like from there, we can work with it. Yep.
Okay, well with that, I'd like to thank Heather, and very interesting talk.